Hi, I'm Peter Davies, and I'm going to be talking about improved deterministic Δ+1 coloring in low-space MPC, joint work with Artachumai and Murat Party. So I'll start off with the MPC model. It's a parallel computation model where we're given some large input graph with n nodes, m edges, and maximum degree delta. And we need to try and solve some problem on this graph by applying a collection of machines to do processing in parallel. Now, the restriction on these, the reason why we can't just use one machine, is that they have a space-bound S, which is lower than the input size, so we can't store the whole input on one machine. And actually, we're looking at the low-space MPC model, which is the more restrictive variant, where this space-bound S is sublinear in the number of nodes in the input graph. So we can't even store a list of all the nodes of the input graph on one machine. Space-bound is n to the epsilon for some arbitrarily small positive constant epsilon. Okay, how many machines are we allowed? Well, the minimum possible we could use would be enough to fit the input across our total space. By total space, I just mean the sum over all machines of the space-bound S, which would be n plus m over s machines. We actually are going to use slightly more than that. We use n plus m over s machines, so n to the 1 plus epsilon plus m total space, for the reason that that actually gives us a lot more power, means we can do a lot more and get faster algorithms in the model without very much additional space. Okay, how does an MPC algorithm proceed? Well, to start off with, we get our input graph partitioned arbitrarily among the space on our machines. And then each machine can do some computation on the local data that's stored on it. Then we have a communication round where each machine can send messages to any or all of the other machines. Then again, they can do some computation on the information they have now. And then we have another communication round and so on. And the only limitation here is this space-bound S. So the computation that's done by each machine has to be bounded by S space, and also the total amount of input and output that each machine sends and receives in each communication round has to be bounded by S. There's no further restriction on that you can't send it all to one machine. You can send it all to one machine, or you can spread it among multiple machines, but in total it has to be bounded by S. And our goal is then, as algorithm designers, to just design an algorithm that allows us to solve the problem using the minimum number of communication rounds. So the problem we're going to be looking at is a classic one of Δ+1 coloring. We have our input graph, and for each node of the input graph, we have a choice of colors. And to solve the problem, our output needs to assign each node a color such that no edge has both its endpoints colored the same, so a proper coloring. Okay, now actually we can solve the more general problem of Δ+1 list coloring with this algorithm, where each node gets as input a palette of colors, and these palettes don't have to be the same. They still have to be of size Δ+1 where delta is the maximum degree, but they don't have to be the same in list coloring. But for simplicity in this talk, I'll just talk about Δ+1 coloring where these are the same as we see on the left diagram there. Okay, so that's the goal with our algorithm. What's known in low space MPC? Well, the starting point, the kind of basic algorithm, is just a simple randomized algorithm of each node just picks a random color from its palette, tries to color itself, communicates with its neighbors to see if any of them pick the same color. And if none of them pick the same color, it's safe to color itself that color. So it does so and remove itself from the graph. Okay, and if you analyze this in a straightforward fashion, you'll see that it colors all the nodes in log n rounds with high probability. The way I described it, that was actually more of a local algorithm, though. It's actually not completely trivial to implement this in low space MPC, because, as I said, we can't fit a node's neighborhood or its palette in our space bound of S. They could be of size up to n, which is larger than S. But nevertheless, you can implement this fairly straightforwardly just by assigning each node a collection of machines devoted to it rather than a single machine. And you can get a simple log n round algorithm in low space MPC. Okay, then recently there was, well, fairly recently, there was a much better algorithm, a triple log n algorithm by Chang et al. And they got this by adapting the best local algorithm for coloring of Chang, Li, and Petty, which I've written here, adapting it to the MPC model and actually speeding it up by a logarithmic factor, which we'll talk about more later. The reason why the running time of the local algorithm of Chang, Li, and Petty is written like this, even though this log star delta factor is very small and is always subsumed by the polylog log n factor, is that it consists of two different halves. So the first procedure in it is randomized. It's very quick, takes log star delta rounds. And after this randomized procedure, you can show that your graph has shattered into small components. And then you apply a deterministic procedure to this shattered graph which is based on the network decomposition result of Boswell and Grafari, and gives you a poly log n round algorithm to color the remaining shadow graph. Okay, so that's the randomized algorithms. Deterministic algorithms in low space MPC. There is only really one we gave ourselves last year in this paper, which is actually primarily for linear space MPC and congested clique, which are related models, but you actually have a lot more power and can in fact get constant round algorithms there with more space, linear space on your machines. But as a kind of side effect, we also get a log delta plus log n round algorithm for low space MPC, deterministic algorithm, which is really the only deterministic algorithm specifically designed for low space MPC. So there's still quite a big gap here between that running time and the triple log n of Chang et al. And the goal in this work was to try and improve deterministic algorithms for low space MPC. Okay, so I'll talk more about how the randomized algorithm works and how we could make that deterministic. So there are 4 main steps for the randomized algorithm of Chang et al. The first is a randomized partitioning procedure that takes the input graph and divides it into a collection of instances, each of which has much smaller maximum degree, polynomially smaller, in fact, than the space bound on each machine. And if you can solve all of these instances, then you can solve the whole thing actually in no asymptotically longer time. And the reason this is useful is that if you reduce your degree below the space bound, you now can store neighborhoods, and in fact, neighborhoods even of larger radius on single machines. And that allows you to simulate this randomized part of the Chang-Lee-Petty algorithm, essentially round by round. So basically, you assign each node a machine, and that machine does for this node exactly what the node would be doing in the local model, the local algorithm of CLP. Sends all the messages to the other nodes that will be sent in the local algorithm, and receives the messages that would be received in the local algorithm, and does the computation that you would do in the local algorithm of CLP. Okay, so the running time here is the same as the shattering, pre-shattering part of CLP, log star delta, which is extremely fast. Okay, then you still have the deterministic post-shattering part of CLP, and this is the part that can be sped up in MPC. So this is actually sped up by a logarithmic factor, for the reason that we have this quite powerful graph exponentiation technique in low space MPC. So how this works is that in the local model, we need to run a polylog n round deterministic algorithm. That corresponds to being able to make our decision for the output of each node, seeing a polylog n radius neighborhood. That's a well-known equivalence in the local model. And we can collect a polylog n radius neighborhood in triple log n rounds in low space MPC by the process of graph exponentiation, which is roughly that you collect all the 1-hop neighborhoods of each node onto machines, and then you can combine those together to collect the 2-hop neighborhoods, and then combine those to collect the 4-hop neighborhoods, and so on. So you get a logarithmic speed up in this neighborhood collection procedure, which is what we need to do here. Once you've collected these neighborhoods in triple log n rounds, you can just simulate the deterministic algorithm, the deterministic post-shattering part of CLP immediately, and get your final output. Okay, so that's how the algorithm of Chang et al. Worked in low space MPC. How can we make this deterministic? Well, the first observation is that the 3rd and 4th steps here are already deterministic. We don't have to do anything. Graph exponentiation is deterministic, and obviously the deterministic post-shattering part of CLP is also deterministic. So those are already done. We don't need to do anything there. The second observation is that in our paper from last year on linear space MPC and congested clique, we essentially de-randomized already this randomized partitioning procedure to reduce degrees to this smaller than the space bound S. We do have to make some tweaks actually in this paper to get some guarantees that we need to run CLP. It's not exactly the same, it's slightly different, but essentially this is already done. We can do this using hash function, which I'll talk about later, bounded independence hash functions. So really the only thing that remained as a major technical obstacle was to de-randomize this randomized part of Chang-Lee-Petty's algorithm. Okay, and that's what most of the paper spent time on and what we're going to spend time on for the rest of this talk. How can we de-randomize the randomized part of the Chang-Lee-Petty algorithm? Okay, so what would we start off trying to do? Well, a standard de-randomization technique is to use bounded independence hash functions. And this is what we used in our paper from last year on linear space MPC. And this is essentially a means of reducing the amount of randomness you require for a randomized algorithm by showing that actually the analysis still works if you don't need all of your random choices to be independent, but you only need some much smaller amount of them to be independent at one time. If you can show this, if your algorithm still works under bounded independence, then you can replace your full string of random bits by a much smaller random hash function from a family of bounded independence hash functions, thereby reducing the randomness you need. And then you can search the space of these much shorter random seeds you need efficiently via the method of conditional expectations to fix one that works deterministically in some small amount of time. Okay, and this essentially is the method that we used to get constant round linear space MPC algorithms for coloring. So can we use that here? The answer turns out to be no. There are some obvious obstacles that mean that this doesn't seem to work for de-randomizing Chang-Lee-Petty's algorithm, and that's what I'll be talking about now. So what happens if you try and use bounded independence hash functions to de-randomize Chang-Lee and Petty's algorithm? So I won't give a full description of what their algorithm is because it's very complicated. This is a graphic depiction of their algorithm, but it has two main parts that I'm going to talk about. One part is that they have a procedure for coloring locally sparse nodes, which means nodes whose neighborhoods contain a lot of non-edges. And this procedure is something quite similar to what I mentioned as being the kind of basic coloring procedure where you just try and color yourself with a random color. They can show that this generates some slack, which means excess colors. You get more colors in your palette than you have remaining uncolored neighbors. And using this, you can color these nodes very fast. Okay, so that's one of the two main coloring procedures they use. The second one is for coloring locally dense nodes, so the opposite of this property. Nodes that have very few non-edges between their neighbors, so their neighborhood looks a bit like a clique. And this uses a different coloring procedure for dense coloring, where essentially these neighbors that look almost like cliques, you can actually you can make that formal and find that you can decompose this into structures called almost cliques. And then within these almost cliques, you can synchronize all your random decisions. So you can make sure that when you're trying colors, within these almost cliques, you're synchronizing everything so that none of your color choices there are going to clash. The only clashes are possibly between your almost clique and a different almost clique, of which they can show there are a few. Now, you don't really need to understand how these works, but the important thing is that this first procedure for coloring locally sparse nodes probably works using bounded independence. I say probably because this isn't what we ended up doing, but almost certainly it would have worked. It seems like the type of procedure where the analysis should be very amenable to using only bounded independence. But this dense coloring procedure seems to require very high independence. It doesn't seem like you should be able to use bounded independence for that because kind of by design, you need your random choices to be very highly correlated with each other, coordinated with each other to avoid these clashes within almost cliques. You can't do that seemingly with only bounded independence. So we can't really use our tool of bounded independence hash functions here. Instead, we use a different tool. And the tool we're going to use is pseudorandom generators. So what are pseudorandom generators? Well, again, they're a means of turning a short string of random bits into a much longer string of pseudorandom bits. So in a way, reducing the amount of randomness we use. By pseudorandom here, I just mean that a polynomial timed computation can't tell that these aren't random up to some amount of error. Okay, so these look the same up to some error parameter delta as random bits for any polynomial time computation. And there is the first thing you see when you look up pseudorandom generators is that there exists a quite simple optimal pseudorandom generator that has this expression for how many random bits you need, which is quite short. And that would be okay for us, that would be fine. That seems like it would be a good thing to use. So the way we would want to use this is to take all of these possible short seeds, plug them into our pseudorandom generator, get long strings of pseudorandom bits, use those for the randomness in the Chang-Lee-Petty algorithm, and hopefully these work very much like random bits, so we get the same guarantees as Chang-Lee and Petty do. And then we just agree on one of the seeds that actually worked, which is quite easy to do in low space MPC. And then we've de-randomized the algorithm. But there are a couple of problems with this, and there's a reason why this pseudorandom generator isn't really used, especially in sequential computation, which I'm going to talk about now. The first problem is that this construction of the pseudorandom generator isn't an explicit construction. It's some kind of counting argument, which means that we can't explicitly construct the PRG using a efficient algorithm. Okay, and that means either we have to hard code the pseudorandom generator into the machine's memory, which means that we have to use non-uniform algorithms that depend on the input size, or we can compute it, but it takes exponential computation. So we have two options here. We can either use exponential computation, or we can have non-uniform algorithms. And basically what we do about this is just that we accept that we have to use one of those things. I mean, this doesn't kill MPC algorithms, because really in MPC algorithms, we care about the space bound, and this does still respect the space bound. So this is a bit of a downside, and it's still an open problem to see whether we can get uniform algorithms that use polynomial computation that can still do this. But for now, we'll just accept that this is what we need. But there's still another problem. And the other problem is that we have to be able to actually fit these pseudorandom generators on our machine space in order to use them. Okay, and the size of these PRGs is this expression. I don't really expect you to have followed what all these parameters mean. But the upshot of this is that if we set these parameters so that the machines can store the pseudorandom generator, then we get some error probability, which is something like, say, n to the minus 0.01. Okay, so it's a fairly low error probability, but it's much weaker than an error probability with high probability success. Okay, and what that means is that if we apply this PRG, we get this error probability at every node. And that means that if we try and run Chang-Lee-Petty's algorithm, say n to the 0.99 nodes won't satisfy the properties that CLP guarantees with high probability. Still a significant number of nodes that essentially fail and don't work as CLP says they should. Okay, so we have this failure probability. What can we do about it? And this is the main technical part of our paper. It's quite a long amount of technical work, so I'm just going to mention briefly the main ideas that we use to deal with this. So as I say, the first, if we apply our PRG, we get some of the nodes failing. What we want to do is just rerun the algorithm on the failed nodes. So take the coloring of the nodes that succeeded and run the algorithm again on the nodes that failed to recolor them. Okay, and if we do this a constant number of times, actually, then we color all the nodes, because every time the number of nodes that fails is like a polynomial smaller than the total number of nodes. And if we, in this case, apply it 100 times, we color all the nodes. But we can't actually do this immediately, because CLP involves quite close control over several invariants that have to be satisfied. It's not an algorithm for degree +1 list coloring. So you can't apply this to any coloring procedure. You need to actually satisfy some invariants. And we have no guarantee that we do this anymore. Our PRG, when it breaks, can break badly, and it can break these invariants, which means that the analysis of CLP no longer holds. Okay, so we can't just run CLP, uncolor the ones that failed, the nodes that failed, and run CLP again on those. That breaks everything and means that the analysis no longer works. So how do we get around this? So we have two main ideas that we use at various different stages of derandomizing the CLP algorithm. The first is to use a mixture of hash functions of PRGs. So I told you that the dense coloring part of CLP doesn't really work using bounded independence, but some aspects of it do. And these bounded independence hash functions don't have this error that we get from using the PRG. So by combining the two, we can sometimes get the best of both worlds. Okay, so that's the first idea. And the second idea is that we can use a more complicated set of invariants to control what's happening with tolerances, essentially. So we can show that even though we do break the invariance of CLP by trying to repeatedly apply the algorithm using this PRG to the remaining set of failed nodes, we don't break it too much. We break it within an amount that we can actually tolerate if we use some more sophisticated set of invariants. Okay, so as I said, this gets very technical. That's all the detail I'll go into for now. All I wanted to say to sum up is that these combination of techniques allows us to de-randomize the randomized algorithm of Chang et al. At no asymptotic extra cost. So we match the randomized running time with a deterministic algorithm. But there is this caveat that it's either non-uniform or it uses exponential computation. So it's still an open question whether you can match this very fast running time with a uniform algorithm that uses only polynomial computation. Okay, so thank you, and hopefully I'll see you at the live talk to answer any questions. Thanks.